So today I'm going to continue the discussion of the path integral formulation of quantum mechanics. So non-relativistic system, mostly on the simple example of the particle in one dimension. But that's in order to illustrate the power of the method. So I'm going to continue and finish to discuss the concept of what is path integral, well, let's say quantum mechanics and path integral at imaginary time. That imaginary time, sorry, that we started yesterday. And this is going to illustrate the relation between, in particular, the relation between quantum mechanics and statistical mechanics of classical 1D system. The classical is very important. And, well, a bit later. Then I'm going to discuss how in path integrals you illustrate the observable, namely operators, and what's called correlation functions. Because up to now we have only discussed how to formulate the evolution operator, the quantum dynamics of the system in terms of path integrals. And I'm going to discuss also, well, very shortly, the issue of semi-classical. We discussed that already, semi-classical approximation. And if time, I'll start to discuss, but I don't think I'm going to have time. I'll start to discuss the quantum field theory case in the case of the Klein-Gordon field. But I don't think I'm going to have time. Okay, so remember what we did last time. Well, I derived shortly, but I show that if you consider the matrix element of a quantum mechanical system so the matrix element, so sometimes it's often called the propagator. So I'm going to call this Qi, Qf, T. This is propagator. So that's the probability amplitude to have a particle at initial position Qi and at final position Qf when it evolves during a time t. Okay? And that's for a particle in the potential, so the Hamiltonian is p squared over 2m plus v of q. And we have seen that this can be written as a path integral, a sum over all possible trajectories that starts at time 0, let's say, or time t initial to the initial position at the final time Tf, its end at the final position. So you sum over all histories, exponential, and you have an I over S times the classical action of this trajectory, where the classical action, so this is the Hamiltonian, and the action is S of q equal integral from 0 to, well, let's say, t initial to t final of ds m over 2 q dot squared minus v of q. This is classical action. Okay. So the picture is this one. As a function of time, at initial time, the particle sits here. At final time, the particle is here. And you sum over all possible histories. Well, we in some class of histories that I'm going to discuss a bit later. Okay. So this was the first thing, and we have seen that if you consider now that time is a complex, so we are discussing the mathematical properties of this object or the evolution operator when time is considered as a mathematical complex variable. We have seen that this is u of t is bounded. It's a bounded operator in the lower half plane. So this is real time, and this is imaginary time. So in the lower half plane, when imaginary part of the time variable is less or equal to 0, this is bounded. And we have seen in particular that when t is equal to minus I tau, with tau positive and real, of course, just by analytic continuation, u of minus I tau is exponential of minus tau over h bar times the Hamiltonian, which looks like the unnormalized partition function of the system at finite temperature. So it's the very system of a quantum particle in a potential well V. Okay, so we have seen that there is and we call this the Euclidean evolution operator, just because when time is real, tau can be considered as an Euclidean time with a positive signature instead of negative signature. So that's just a mathematical terminology at that stage. And so going from there to there is called a Wick rotation. And so we have seen that, in particular, the partition function of the system at finite temperature, so we can make this dictionary between the Euclidean time and the temperature. That's a classical, that's a temperature. And Z is just the partition function of the system and a Gibbs state at temperature T, given by this important relation, is just, of course, a trace of UE of tau. Okay. So now the question is, this is a definition, just a very easy definition in terms of operators. And is there a path integral formulation for the matrix element of the Euclidean, so the unnormalized density matrix? So the question is there a path integral for this? Okay. And in fact, the answer is yes. Because you can take this formula and just make this Wick rotation and see what the result is. And that's what I'm going to do. So I'm just going to be a bit naive and just take the formal continuous formula for the path integral and make a Wick rotation. But you can repeat more precisely the steps that we have been using in deriving by time slicing and taking continuum limit of the evolution operator, and this is going to give the same result. So I'm going to. So what is path integral at Euclidean time? So we want to compute something. Let me call this the Euclidean propagator. So I start from an initial position and end up at the final position, and simply now time is Euclidean. So this is a matrix element between initial and final position states, of EU of tau. Okay, so now think about what's going on if you make a Wick rotation in the path integral. So if you want, instead of doing this, we consider path integral where now this is Euclidean time. But so you go from 0 to tau. This is Euclidean time. And you start from the same initial and final configuration. Okay. So since t is a variable, you just have to consider now paths. Paths that depends on an Euclidean time variable sigma. So let's call it sigma instead of s here. This is an integral over s. So q of sigma is a trajectory in Euclidean time. Okay? And so we make an analytic continuation, if you want, of this whole trajectory in the time complex variable and just rotate it in complex, going from real time to imaginary time. Okay. So we see what comes from, what does this become? So the action becomes an integral from, let's say, sigma initial or tau initial to tau final, with, of course, tau equal tau final minus tau initial of, now I change, so I make the change of variable, this Wick rotation, so I'm writing that the original S variable is now minus I sigma. So I make a change of variable, and therefore I get minus I times d sigma. Okay. Now, by Wick rotation, so Q of S becomes Q of sigma. Okay. But of course, Q dot of S, which is the derivative with respect to S of Q, becomes, if you are a bit naive, just 1 over minus I, so I times Q dot of sigma, when Q now is a function of sigma, because you made a complex change of variable. Okay, so you get I Q dot of sigma squared times m divided by 2. This is for the first term. And now the second term becomes still is minus v of q of sigma, because there are no derivative. So the actions transforms into this. So you see that the term, the phase, the quantum phase in the path integrals becomes exponential of I over h bar minus I integral d sigma of minus q dot of sigma squared m divided by 2 minus v of q of sigma. Okay, that's, so this gives a factor 1 and this gives a factor minus 1, so this becomes exponential of minus 1 over h bar integral over d sigma from m over 2 q dot squared of sigma plus v of q of sigma. Okay, from the initial time tau initial to tau final, or if you prefer, from 0 to tau. Okay. So you see that this, by this naive Wick rotation, the phase exponential I over h bar, the classical action, becomes the exponential of minus something which is bounded from below. it looks like an energy. It's a kinetic energy plus a potential energy. But that's for a trajectory that evolves in Euclidean time. So this is not a physical trajectory of a particle, but it's similar to the Hamiltonian. Okay. Okay. So this is for the what becomes a quantum phase. Now, what is the measure in the path integral? So this is for the action. How does the measure behave? The measure is this d of q was formally a product of a time, sigma, of dq of sigma, and there was a 2I pi h bar over m times an epsilon, where epsilon was a delta sigma when you were discretizing the equation, to the power minus 1/2 for each sigma. Okay, formally. So now, if you perform a Wick rotation, you expect that this becomes products of S. I'm sorry, this was the path integral at real time. So if we make the Wick rotation, this becomes a product of a sigma formally of dq of sigma. But then, if we make a Wick rotation, if you think about making a Wick rotation here, it means that you are discretizing, you are making a Wick rotation and discretizing time. So since sigma is I times S, so epsilon was delta S, the time step interval. So epsilon becomes minus I times delta sigma. So it becomes minus I times delta sigma, the Euclidean time step. Okay? And so this becomes 2I times minus I, so this becomes 2 pi h bar over m times epsilon Euclidean, if you want, minus 1/2. So delta sigma is what I'll call epsilon Euclidean. Okay. So this is what becomes a measure. Okay. So the idea now is that when you perform Wick rotation, what you have to do is to consider all trajectories between the same initial and final condition, but now you discretized by a delta factor epsilon Euclidean equal delta sigma, the time step integral. You use this discretized measure, and you use as a weighting factor for the integrals this one, this phase factor, which is not a phase anymore, but just a number, and a positive number, because it's the exponential of minus something which is real. So this is a positive weight for this configuration. So the final results that I just derive in a very, very sketchy way is that this object, Ke of Qi, Qf tau, is expected to be, well, formally, the limit with this measure that I'm going to call the Euclidean measure of a Euclidean trajectory, dE of Q. So this is the Euclidean measure, defined this way. Okay. Times exponential, and this factor, well, since this is analog of this, let's call this the Euclidean action of an Euclidean trajectory. So what I'm calling the Euclidean action is this factor. Okay? And therefore, the weight associated to any Euclidean trajectory is exponential of minus 1 over h bar S Euclidean of this Euclidean trajectory, with Q of sigma initial or tau initial, let's say, is Q initial, and Q of tau final is Q final. So the boundary conditions have not changed. So we sum over the same set of trajectory, but now to each trajectory is associated an Euclidean action, a weight which is exponential of minus 1 over h bar times the Euclidean action, and a measure which is now a real measure. So this is the Euclidean measure. Okay. See? So this is the final results for Euclidean path integral. Okay, yes?
So in order to perform the mutual function, do we need at least one of the initial and final times to be finite?
I think better to do that because, well, I think you can do that for, you mean at time at infinity?
Yeah, if both are infinity, then...
Yeah, you can make a Wick rotation in space, something like that, going from minus infinity to plus infinity, like that. From minus I, well, plus I infinity to minus I infinity. Yes, you can do that. I think so. But, well, I'm going to discuss that a bit at the end of this lecture. So what's happened when you take the limit where time goes to infinity? But you can do that formally. Yes?
We have only reasons why the time evolution operator would be bounded in the lower half plane, and the upper half plane is going to blow up.
That's what I explained yesterday. That's because, in general, in particular, I'm considering a particle, you see, in infinite space, one-dimensional but infinite space, and in a potential. So the particle, I have Q, I have a potential, which may be complicated potential. So the energy level, or if you want, H is bounded.
Yeah, I know why it's bounded, but my point is, if you integrate from minus infinity to infinity, then you Wick rotate.
Yes.
Like the upper half plane is in the part. And once the upper half plane,
no, that's because
everything blows up.
Okay, I understand your question. No, that's because in fact I've been considering what's happening if you are at finite time, t finite, and positive. Then basically you start from the origin and you go to time t. So the rotation is around the origin. So if you go from minus I infinity to plus I infinity, you should rotate starting from there. But which is a bit difficult to represent. So that's why I prefer to consider t finite at that stage. I'm going to come back later, so I think rather than trying to make some kind of formal treatment of what's happening when t is infinite, it's better think of what's happening where t is finite or tau is finite, and then take the limit t goes to infinity or tau goes to infinity. Okay? I think at that stage I prefer to just say that. Okay? You're going to see later. Okay. So here we are. We have an analogous definition of what we did at real or physical time for Euclidean time. We have an analog representation in terms of an integral or a sum over all histories for this matrix element, which is number. Okay. And okay, this was a very sketchy definition, but if you like, you can make it clean, make it rigorous by repeating the steps of discretizing and taking the continuum limit. Then we're on safe ground. Okay. Okay. So we have an Euclidean measure, we have an Euclidean action, and we have a similar formula where we, instead of having phase, we have exponential weights. Okay. So now can we go a bit further and compute the partition function? We are interested into, but it came out that the evolution operator at Euclidean time is like the unnormalized density matrix of the quantum system at finite temperature. And so one may ask, what is the partition function z of beta, which is a trace of exponential minus beta h for this system? A particle in a given potential, but in contact with a big thermostat, so that it exchanges energy, and he has some distribution in the different energy states. It's in its energy state with a probability distribution that is given by the Gibbs weight factor. Okay. So that's a partition function of this quantum system at finite temperature. Okay, so we have a path integral representation for all the matrix element of this. It's just above. So we can use this. First, what is a trace? The trace is a sum over the diagonal element in any basis of this operator. So since we have a path integral representation in position space, it's natural to express the trace in terms of a sum over all position eigenstates. So we can use the fact that the trace is just the integral of a q minus infinity plus 1 infinity, because we are in one dimension, of the q times exponential minus beta h. Okay, but now we have a path integral representation for this object, because this is just integral dq times k Euclidean of the same initial and final position at Euclidean time tau, with tau equal h bar times 1 over k Boltzmann t. It's h bar beta, the Boltzmann factor. Okay. And we have a path integral for this. So we get, for this, a path integral of a Euclidean trajectory, exponential minus 1 over h bar, the Euclidean action associated to this trajectory in Euclidean space, in Euclidean time. And what's the difference between this particular and this one is that we enforce that q at the initial time is the same as q at the final term, and we integrate over q. So we have the only constraint on the path is that we have periodic histories, if you want, such that q at origin is equal to q at time tau, with tau given by this relation. So the only constraint is that when we sum of a trajectory in Euclidean time. If you start from this, you must end up there, but you must sum over all trajectories. You can start from any point. The only constraint is that they end up at the same point. You see. So you sum over periodic histories. Yes?
No, another question. Are you assuming that the Hamiltonian is Euclidean time independent?
Pardon?
Are you assuming that the Hamiltonian is Euclidean time independent in this derivation?
What do you mean Euclidean time? Time independent.
Yeah.
Yeah. No, I'm assuming everywhere here, that's a good remark, yes. Here, I'm assuming that H is time independent, yes. Otherwise, well, first, it's much more complicated to define and sometimes not possible to define what is a Wick rotation. And in addition, it doesn't make sense to think about the Gibbs distribution. Because the Gibbs distribution is stationary. And if you study the thermodynamics of a system, in contact with the thermostat, but with an Hamiltonian that varies, of course, in general, you won't have equilibrium distribution. Well, that's a very important class.
So here you're describing a static thermal theory, right?
Yes. Here Gibbs distribution means stationary thermal equilibrium. So Gibbs, it's a very, very special class of statistical distribution, but it's the one which is useful for a lot of systems, because especially just you are interested in how the hair behaves in this room. Usually, it's a good approximation that assuming that it has a finite temperature or temperature changing very, very slowly and adiabatically. Okay, for instance. Okay, so the partition function is just given by the same path integral at Euclidean time, but just with the tradition of periodic histories. So in some sense, in this relation, tau is a period. Period in Euclidean time. You see? So it's not a real period in real time, but it's a period in Euclidean time. So in fact, I'm going to now to write a picture which is a bit formal, but it's a very useful picture to keep in mind. If you are thinking of a quantum system at finite temperature and thermal equilibrium, you must think and interested in, for instance, the dynamics in real time of this system when it is at thermal equilibrium, so in a mixed state. You must think of time as a time which is infinite in the physical time, so it goes to minus infinity to plus infinity. But when you make a Wick rotation, for instance, to use this picture or to study the properties of the density matrix, you must think that you can consider that time becomes imaginary. So time can become Euclidean, but you must not think of this as the half plane, because for all practical purpose, when you are interested in equilibrium properties, you are going to have to compute properties where the time goes back. So you must think of this as something like that. This is tau. This is real time. This is imaginary time, and you must think of you must think of complex time as an infinite cylinder. So it's infinite in the real-time direction, physical time, and it's periodic with a periodicity tau in the imaginary direction. Okay, so that's a think of as living on a cylinder. Periodic in the Euclidean time direction. Okay? And I think you probably have heard about this idea of periodic Euclidean time in one of the lectures or two of the lectures by Dan on statistical mechanics. He mentioned that as far as I've seen on the videos. Okay. So that's something you might be a bit familiar. Okay. So, I think this ends up the discussion that I wanted to discuss about the first discussion I wanted to do about path integrals at imaginary time. Okay. So now, much time do I have left? So I might discuss the relation with classical 1D system, but I'm going to postpone that a bit and go back now. So second point I want to treat today is operators and correlation functions. Okay, because up to now I discussed only how you formulate by a path integral the evolution operator. But of course, in quantum mechanics, you are interested in making measurements and therefore computing matrix element of operator in a given quantum states, and then computing more complicated or subtle. But basically, you want to compute matrix element of some operator A. That's the probability amplitudes. So how do we compute this? So I'm going first to discuss the simplest operator, which is a position operator. Q. Or any function A of Q, where A is some function. So, for instance, a polynomial or a sign. I think I had a question about the sign. Okay. So any operator. So this is an operator which commutes with Q. Okay. So, well, it's quite easy to check what it is, because, in fact, in the position representation of states, what you know is that if you consider a matrix element between some Q and some, let's say Q prime, A of Q, so this is a matrix element between two different position eigenstates of an operator which is a function of Q. Since A of Q commutes with Q, it can be diagonalized in the basis of Q. So this is basically the standard scalar product delta of Q prime minus Q, because this is non-zero only if Q equal, times the function A of the Q, which is now a number. So remember, Q is a state, is a quantum state, but Q is a number. It's a position that labels. So the position labels a quantum state. So this is a function of the position, while this is a function of an operator. Okay. So now, well, I can derive what I want to compute in two ways. So let me just be very stupid and just ask, okay, what's going on if I start from the path integral from d of q exponential I over h bar s of q. So the standard path integrals, that's q initial, t initial equal qi and q at t final equal qf. So the standard path integrals that represent the matrix element of the propagator for at real time. So now I am at real time. And I just insert that I consider that I have this path integral. I start from initial time. I end up at final time. And at a given time t1, so I consider a time t1, which is between t initial and t final, some time, I insert in the path integral the function a of the value of q on the path integral at time t1. So basically, I consider this kind of path integral between the initial and the final states, but at time q1, I measure the position. So of course, this is fixed, but q of t1 is a random variable. So this is a non-trivial, not a completely trivial. So what is this object? Well, you can use this formula by separating this path integral into two path integrals. You separate this path integral as a path integral between q t1 and t initial and t1 times q of t1, and then path integral which is t1 and tf. So it's quite easy to see that this object is nothing but this object here. Well, I should have written it on a blackboard. But this object, okay, this object is nothing but, so this path integral, if you fix q of t1 to be a given q1 if you want, this is just the path integral, so the matrix element between q initial and q1 of u of t1 minus t initial. Okay? This is the path integral. This path integral is q1 u of tf minus t1. I'm sorry. Is it readable? Or is it too small? This is TF. I should write this a bit. Okay, let me write this way. This is Q1. This is Q initial. This is Q1. This is U of T final minus T1. And this is the state Q final. And I write that q of t1 is equal to q1. Since it's a random variable, I can fix q1 and integrate. And then I integrate on q1. So I integrate from minus infinity to plus infinity. And when q of t1 is fixed, I had just a of q of 2, a of q1. So since I integrate over this random variable, I do not need to specify that it's measured at a given time t1. T1 appears in the matrix element of this path integral and this path integral. Okay. But you see, this means that as an operator, you can write the operator a of q as integral over dq1 of q1, that's a projection operator, times the number A of Q1. This is just diagonalization of A. Of the operator A of Q. Okay. So I can rewrite this simply as the matrix element of between QF and Q initial of U of TF minus T1, the operator A, this formula doesn't depend on T1, times U of T1 minus T initial times Y. So this is a matrix element now of an evolution operator times an operator times U of TF. Okay? So this is given by this path integral. Integral D of Q E I or H bar S of Q times A of Q of T1, where here Q is a random variable. Because you integrate over all the possible value of Q. So here Q of T1 is a random variable. And here capital A is an operator, a quantum operator. Okay. So you see, you can represent in the path integral the insertion of an operator at a given time T1 by just inserting a classical but random variable in the path integral. So you have a dictionary between the operator A and inserted at time T1 and the random variable, random but classical variable. Well, let's say the operator Q time T1 and Q at time T1 in the path integral. So you see, so you have a correspondence principle. It's just the path integral version of a correspondence principle in quantization between classical variables and operators. Some kind of correspondence. That's principle. Okay. Good. So keep this procedure in mind. Okay. So this is the way. So keep this. This is the basic formula you need to know. And this is a matrix element with operators in the Schrödinger representation. Okay. And it's interesting to see what this corresponds to as you rewrite this in terms of the Heisenberg representation. So in terms of the Heisenberg representation, we have a U, so we can write this as U of T1 times U dagger of T initial. And this as U of TF times U dagger of T1. So U dagger of Ti times Qi is the initial states Q initial at time T initial in the Heisenberg representation. U of T1 times A times U dagger of T1 is the operator A at time T1 in the Heisenberg representation. And the final state is QF at time T final. So this is the same thing as this one, just two different ways to represent the same number given by the same path integral in the Schrödinger picture and the Heisenberg picture. So you see that the dictionary is in fact that the correspondence principle is that Q of T1 is associated to the operator A, or let's say Q of T1 in the in the Heisenberg representation. So the time at which you insert your observable in the path integral correspond to the time at which you insert the operator here, the position operator, in the Heisenberg representation. So the correspondence between random variable in path integrals and operator is in fact makes a complete sense if you use the Heisenberg representation. Okay? Yes?
One question. The first time we inserted A of Q1
Yes.
there in the box that is with red.
Yes, this one.
And then we pass to the second one, and we have an integration over Q1.
Yes.
Where is that integration?
That's because here you integrate over, you see, think of it in terms of discretizing space.
Okay.
Discretizing time. So when you sum over histories, you sum over all the position
Okay.
possible during the history, including Q of T1. It's nothing special in the measure.
All right.
And nothing is special with respect to Q of T1. Simply, you weight the integration of a Q of T1 by this function A of Q of T1, while it's not weighted by a special weight for the other Qs. You see? You just change the weight of integration of a Q at the specific time T1. Okay? Yes?
Are you assuming normalization of the, say, the integral d of q exponential I by h bar s of q is equal to 1?
Yes. So do you think there is a problem of normalization?
No, I was asking if you are assuming that it's normalized.
Well, I told you I've not changed anything. So the normalization for this and the normalization for this is the same than for the path integral with no insertion of this term. So all normalization, when you compute this, you get this matrix element. There is no overall factor of change in normalization. So that's an exact expression. That's an identity. Okay? So you have this correspondence principle. Okay? Good. Okay? So you see, in some sense, once you have done the work of constructing a path integral for the evolution operator, you get basically for free the operators, other operators. Okay. So this was for position. So position is easy. For momentum operator, it's a bit more complicated. And I might discuss that a bit later. You'll see why there is a little subtlety when you try to define what is a momentum operator in path integral, but it's possible. So there is no difficulty in principle. But I'm going to discuss that a bit later. Okay. Rather than doing that now, I'm going to discuss what's happening if you play the same game but by inserting two functions of the position. So now, what's going on if I'm doing this? So what's happening if I take the same path integral with the same initial condition? T initial is Q initial and Q T final is Q final. I get the same phase factor associated to the path integral, but now between T initial and T final, I consider two intermediate time T1 and T2, and in my path integral, I insert a function A here and a function B here. And let's, for simplicity, consider A of Q and B of Q. So I consider the function A of Q of T1 times B of Q of T2. And A and B are some functions. So, okay. But they do not need to be the same. Okay. Well, you can play the same game by just writing the path integral from there to there, integrating over the intermediate position, get a path integral from there to there, integrating over this second intermediate position, take a right integral, and I won't do the calculation because it's exactly the same. What you get is, for instance, in Heisenberg position, what you get is the matrix element between the states QF at time failure and the states Q initial at time T initial, or A of T1 times B of T2. Okay? Remember, well, that's, I use the standard notation of physicists where usually we write time evolving from left to right, but when we apply an operator to a vector, the operator is to the left of the operator, so the causal order, when you write operator acting on space is in this way, while when we write trajectory, it goes in this way. So this is a causal order. I think as a physicist, most physicists are used to that, but in fact, mathematicians often use the causal order in this way, so that it's consistent. Okay, anyway, for physicists. So this is the physicist course of causal notation. Okay. Okay, so it's quite, I hope you understand that it's easy to see that this corresponds to this, because measuring A of Q of T1, Q of T1 here, and B of Q of T2 here amounts to insert an operator A and operator B. Okay, so this sounds easy. So you see that once you have understood what's going on for one operator, you understand what's going on for two operators. Okay. But for one subtleties, here you see I have assumed that, of course, that T1 is less than T2. It was completely implicit. So this is going on if T1 is less than T2. But in the path integral, well, these are random variables, but numbers, so they commute. So nothing prevents you to consider that T2 is less than T1. So if T2 is less than T1, you have the same picture. But here, if T2 is less than T1, here you insert B before A. So it's the same, exactly the same calculation, but what you get is the matrix element between the initial the final states of B of T2 times A of T1 if T2 is less than T1. Okay. So you see the path integrals, the same path integrals gives us a matrix element of a product of operator, but the operators are automatically ordered in time. So the path integral automatically, if you want, automatically order in time in causal order operators, products of operators. Okay. And you see, if you start from this formula and make an analytic continuation in time for T1 less than T2 to T2 less than T1, you do not get this. You get something different. And that's because we are working in Heisenberg picture. So in the Heisenberg picture, A of T1 and B of T2 do not commute. You see, we are in Heisenberg picture. In the Heisenberg picture, A of T1 and B of T2, but also A of Q and B of Q commute, A of Q of T1 and B of Q of T2 do not commute if T1 is different from T2. And that's simply because the relation between A at reference time 0 and A at time T1 is a product of A with unitary evolution operator, which are exponential of H. And that's because, basically because Q and H do not commute in the Schrödinger picture. The Heisenberg, the Hamiltonian contains P that do not commute to Q. Okay, it's easy to compute this, but it doesn't commute. It's basically proportional to the momentum. Because what's important is the commutator of Q with P squared. Okay. Good. So, but in fact, I think that's an object you have seen already in the QFT1 course. You can group this and this, those two definitions, as the matrix element between the same initial and the same final states of what's called the time-ordered products of the products of A of T1 and B of T2. Now this is defining the time-ordered product. Okay, so take this as a definition. The time-ordered product of the two operators A at time T1 and B at time T2 in the Heisenberg representation is B T2 times A of T1 if T1 is less than T2, and A of T1 times B of T2 if T2 is less than T1. So you ordered early time to the right and later time to the left. So path integrals construct time-ordered products of operator. Okay, by per se. That's the way it is constructed. Okay. Okay. Is it clear? There is nothing very complicated in that, but that's just a deep observation. Okay, and one final result. So we did that for one operator. We did that for one operator. We did that for two operators, and of course you can repeat the game for n operators at n different times. So it's not. Okay, so this generalizes to any product of operators at different times, T1, T2, Tk, let's say. Okay, same. Yes?
The thing with the comma is that's just a notation for time ordering, or?
Yeah, that's a notation because since it's not the time order of a product of two operators, it's a time order product of two operators. So A of T1 and B of T2 have to be considered. So it's my notation. So I take two operators, a pair of operators, and I define another operator which is a time-ordered product of those two operators. So that's why I prefer to use a comma.
Okay.
Just a notation. If I had no comma, I would interpret this as a product of B by A, which is not what I want. So it's a notation.
Wait, why is it not?
Because we have seen that A of T1 times B of T2 is different from B of T2 times A of T1.
Yeah, so if you time order it, you swap the two, no?
Yeah, you swap the two. Yes, but with this notation, the time ordered product of A of T1 and B of T2 is the same as the time ordered product of the pair B of T2 and A of T1.
Yes.
We just have to keep track of the order of the time variable. So it's my notation for the time ordered product. Okay? But I think we speak about the same.
Yeah,
the same thing.
It just looks confusing because that's exactly how you write down the commutator. So it looks like you're taking time of the commutator.
You think that is okay? So let me write this as you prefer. Yes. Yeah. Okay. If you prefer, it's not a commutator. It's just okay. No, I understand. So this is time order of a pair of operators. Yeah. So it's okay. Thank you. I never thought this. Okay. Okay. So, okay. So now let me. So of course you can play the same game with. You can define. So this was at real time, physical time. Okay. So you can play the same game with Euclidean time. It's not very complicated. So, for instance, now, if let's go back to the same quantum system at finite temperature, and we are interested in some operator A, which is A of Q, a function Q, okay? And we are in a steady state thermal equilibrium. We are interested in what is the expectation value of the operator A in a Gibbs state characterized by the temperature, by the Boltzmann factor beta. Yes?
It's what happens when you consider two or more operators acting at the same time. That's not necessarily correct.
When you apply this operator and this operator at the same time, okay. I have no problem because if A and B have some function of Q, they commute at the same time. So then the time ordered product is unambiguously defined at the same time. If at the same time the operator A and B do not commute, then the definition of a time ordered product is not ambiguously. You must specify at the same time how you define the products of operator. So time ordering operation, applies where you have different time. But of course, if you consider products of two operators at the same time, you have to specify which operator you are considering. Okay? Yes?
But in this example, aren't A and B just functions of the operator Q?
Yes.
In this example, A and B are just
yeah, that's the example. But if you had a representation for another operator, like the function of the position at different time, you would get the same thing. I can, I'm going to show you just how you define a single P operator, but a bit later. Okay, so let me go back to the Gibbs state. So Gibbs state is a state characterized by a density matrix. So beta is 1 over kBT, temperature, T, and so what is the definition of this? Is we consider what is the average expectation value when you measure, you make a projective measurement of some operator A, but you are in a Gibbs state beta. So this is just by definition the trace of the products of the density matrix rho characterized by the Gibbs state times A. With some density matrix is just 1 over Z times Z beta times exponential of minus beta times the Hamiltonian, and where this is a partition function. Z beta is trace of exponential of minus beta h. Okay? And we have seen that this can be represented as a path integral exponential minus 1 over h bar s. So with Euclidean action on periodic trajectories with period tau related by this. So we can represent this by the Euclidean path integral. Okay? So this is 1 over z beta times the trace of exponential minus beta h times the operator A. Well, we can play the same game that what we did here. This object can be written, so this trace can be written as integral over dq, the matrix element of q, exponential minus beta h times A of q times q. Remember, A is just here diagonal in the q basis, so it's a function of q. But I can rewrite this, obviously, as integral of dq, A of the function q, of the number q, random variable, times q exponential minus beta h q. Precisely because the A of q can be written in diagonal basis as a integral of a q projection operator times A of q, where q is a number. Okay? And this is given by a path integral, by the very same path integral, but with initial and final boundary conditions specified by q. So finally, what you get is this can be represented as a path integral, where you have a path integral of a Euclidean momenta with q, du of q, where q at time 0 is q at the finite time tau, with tau given by this result. So periodic trajectories, periodic histories in Euclidean time, exponential of minus 1 over h bar, the Euclidean action associated to this trajectory. So this is how you represent this object where q is fixed. And here you insert A of q of 0, the initial time. So you see? And you normalize this by 1 over z beta, which is given by the same ratio. So let's say normalize this by the same du of q exponential minus 1 over h bar se of q. Okay, so the same path integral with periodic trajectory. Okay, but simply you have not inserted the random variable, the function A of the position q of the history at time 0.
Sorry, can you repeat what we insert when we have A of q at time 0?
That's because this is a position of the particle at initial time, which is the same as the position of the particle at final time. So simply, the difference between I am in Euclidean time sigma, I go from time 0 to time tau, given by this relation between tau and the temperature. I integrate, so this is q. I integrate over periodic histories, where you end up at the same point that you started from, but simply you cannot choose with a uniform probability q to be anywhere on the real line because this is weighted by a of q. So there is a weight here, weighted by a of q. But here the q, in this formula, q is q at time 0. So that's why I inserted a of q at time 0. Okay? Is this clear?
I'll think about it. Something confused me still.
What?
I'll just think about it.
Yeah, no,
Okay.
okay. So just think about it. But the point is that in this formula, you see, if I want to write this, I can write this by this path integral where eq of 0 is q of tau equal q. And then you integrate over q. Just go back to what I did there. And what I wrote here. First, you write a path integral where the initial and the final positions are q and are fixed, and then you integrate over q. And once you integrate over q, well, this initial and final position are treated on the same footing that the other initial condition, the other position at intermediate Euclidean time, except that there is this weight a of q for the initial position, which is the same as the final position. Okay? See? Good. So we have an Euclidean path integral representation for the matrix element of a single operator in a Gibbs state. You get this equal this. It starts to be a big formula, but this is the path integral representation for this expectation value. Okay? So you can now think about the picture I drew at the beginning of the lecture. You have this infinite time, this time which is infinite in real time and periodic in imaginary time. And simply what you insert is that at the original time you insert a of q here in the path integral. Okay. Now, of course, since time is periodic, Euclidean time is periodic. In fact, you could have weighted the trajectory by the value a of q at any other time, because you can just make a global rotation. So in fact, this doesn't depend on the time here. You see, you could have replaced, one could replace a of q at time 0 by any a of q at time sigma, some intermediate time between 0 and tau. This wouldn't change the result, because it corresponds simply to make a shift in the definition of Euclidean time.
Would you then have to shift the limits of integration as well?
No, because it's periodic. So I'm just taking the fact that if I have a periodic function, for instance, a sine, let's say, like that, between 0 and tau, if now I change my origin notation here, it's still periodic.
Yeah, that's what I mean, like you're changing where you're integrating from into.
Yeah, but it doesn't means any difference, because integrating of a periodic of all possible periodic function between 0 and tau is the same that integrating over all the periodic function between sigma and sigma plus tau for any tau. Okay? So since the path integral is over Euclidean periodic trajectory in Euclidean time, it doesn't depend on the origin. It's exactly like in geometry. When you define a circle in classical geometry, You don't have to specify what is the origin on the circle. Yes?
So before we did statistical mechanics, but we were doing like QFT, you have an interpretation of at what time you're evaluating stuff.
Yes.
But now you're in imaginary time. So I
Yes,
don't know
but-
that. So that's
yes.
the position along the chain.
The position has certain but time. Now we are computing things in imaginary time.
Yes.
But
Yeah,
that's
what
it.
does imaginary time mean? That's like the.
Well, here it's a
position.
mathematical. Here it's a mathematical definition. It's a mathematical object.
You're evaluating A in
Ah, yeah.
Q in some point.
Yeah, you can view this as a path integral where you evaluate A at some imaginary time.
How do you choose which one?
What I said is that for this particular point, this is not important where you evaluate it, because the result is the same.
It doesn't matter. So my question is not
Yes.
like,
No, but if you had, for instance, a system which was not time, if you had a state which was not time, time invariant, not stationary, then this would become important. But for the very specific and simple case that I'm considering of a Gibbs state, then it's independent.
okay, there's
Because
a
it's-
good reason to only think of Gibbs states because they're interesting and stuff. But even in a Gibbs state, you still don't want to only be able to evaluate expectation values of single objects. You also
No.
want to
No.
evaluate products.
Yes.
And if you evaluate the product, it does matter at what you can't use your
Yes,
translation invariance.
you are right. Yes, you are right.
So what do you do then? What does imaginary time mean? You have to pick an
okay,
imaginary
so-
time to evaluate it.
So what you can do, I've used my blackboard. What you can do, well, first you can just treat things as saying I'm doing math. So, for instance, you may compute in the Gibbs state, let's consider, you may consider in the Gibbs state the products of two operators. You have an operator A at Euclidean time sigma 1, and the product B at Euclidean time sigma 2. And this is going to be given by 1 over z beta times the same kind of path integral, E minus 1 over beta S Q times A of Q at time sigma 1, B of Q at time sigma 2. So just take this as a mathematical function defined by this path integral.
Yes. But why am I interested in that function?
Well, why?
Yeah.
Okay, I'm going. Okay. Well, I'll say that before. First, let's just consider this as a mathematical object you have defined by this path integral. Now, first, this makes sense, which means that this path integral is convergent, gives something well defined, only if sigma 2 is larger than sigma 1. So it means that in this path integral of a periodic time, sigma 1 is here, and sigma 2 is here. So here, and that's because if you think about this, this corresponds to the expectation value of the trace of U Euclidean sigma 1, A U Euclidean of sigma 2 minus sigma 1 times B, and then you insert U Euclidean of tau minus sigma 2. You see? If you take this path integral and consider which expectation value operators.
You're putting a meaning to the left-hand side that you just said that was a definition.
Yeah, no. If I
What's the definition of the left-hand side?
define this by this path integral,
Yes.
and try to, in terms of, since we have this equivalence between path integrals and evolution operators, and since this is a path integral at Euclidean time, we are considering Euclidean evolution operator. This object, if I unwind the dictionary I did before, you end up with this matrix element, trace of UE of sigma 1 times A times UE of sigma 2 minus sigma 1 times B times UE of tau minus sigma 2, because I go from the origin to sigma 1, I insert A, I go from sigma 1 to sigma 2, I insert B, and then I continue to hand back another trace.
But I can also make sense of that path integral of sigma 2 is smaller than sigma 1 just by flipping the 2, because in there everything commutes.
No, if you consider that sigma 2 is different from sigma 1, then you are considering the excitation value of B of sigma 2 times A of sigma 1, which is not the same.
You define the left-hand side as being
Yes.
per definition the right-hand side. On the right-hand side I can commute everything. So on the left-hand side I can commute everything. If that's the definition.
No, because
commute them.
here, think here these are operators. So they do not necessarily commute.
There in the path integral they do, and you define the left-hand side per definition as the right-hand side. In the right-hand side they commute.
Yeah,
The
so-
right-hand side makes sense for any sigma 1 and any sigma 2 as long as they're different. They just can't be equal, but which one's smaller or bigger doesn't matter.
Okay, no, I see. But no, what you are considering is that you are starting to consider this case and considering what is time ordering in Euclidean time. So if you want to, you are defining what is time ordering in Euclidean time. So it starts to become formal, but you are perfectly right.
Okay.
But what I mean is that this is different from what I would call B of sigma 2 times A of sigma 1, while sigma 2 is still, larger than sigma 1. So you must be careful about the time ordering when you are considering path integral in Euclidean time. And that's simply because UE of sigma is defined only if sigma is positive. It's not defined if sigma is negative.
So your point is just that thing that you call the definition there
Yes.
is you only use that as a definition
Yes.
if sigma 2 is bigger than sigma 1.
Yes, that's what
It's
I
not the consequence.
Yeah, that's because in some sense, if you are doing a path integral like that, you cannot go back in time, and this is forbidden. Forbidden in Euclidean time. Because the evolution operator at Euclidean time is not well defined if sigma is negative. So one has to be careful. But this makes sense. So I think we agree. Simply, one has to be. It just means that one has to be careful. Okay. So it's a bit. Okay. So this lecture was a bit formal, but I hope you got the picture. And well, it's time to stop. So next time, I'll discuss a bit semi-classical approximation and a bit more what the kind of trajectory looks like in path integral, because here I've been doing a lot of formula. I have not computed anything, basically. And then we start to apply this to quantum field theory, for the real stuff, for us. Because of course you could have or maybe you are going to have a full course of quantum mechanics, non-relativistic quantum mechanics, or you could discuss application of this path integral formalism to semi-classical approximation, what's called trace formula, or the role of semi-classical classical trajectory when you are computing the properties of quantum systems. There is a lot of beautiful physics and beautiful math associated to that, but I want to do it. And I think in the tutorials we are going to start to use this to perform calculation about the correlation function. Because of course, this is called in substance a correlation function by analogy with what you have seen in QFT1. It's a matrix element products of operators. Yeah, I have that. I'm going also to discuss where the ground states, how the ground states appear. Okay, so but that's for tomorrow. Okay, thank you.